Hello everyone, welcome back to Network Security Assignment Series. Let me start this assignment by giving you a critical warning. AI will give you wrong code in this assignment. This isn't a maybe, this is a certainty. AI tools like ChatGPT, Copilot, Gemini, Google's anti-gravity, all of them fundamentally cannot reason about concurrent execution. They see code as sequential statements. They don't understand what happens when two threads execute the same code simultaneously. When you ask AI to make your code thread safe, it will confidently give you code with race conditions, code that looks correct, code that passes a test sometimes, code that randomly fails under load. This is the hardest assignment in this course. It's also the most important because in real world you will use AI and you must know when AI is actively dangerous. By completing this assignment, you will understand race conditions at a deep, intuitive level and then learn to identify when AI suggestions are actively harmful, write thread-safe code manually with understanding and not pattern matching, debug non-deterministic failures under load, test concurrent code rigorously, one running tests once proves nothing, you have to run it multiple times, and also know when to reject AI suggestions completely. This assignment, in this assignment, AI is not your assistant. AI is a hazard you must navigate around. First, let us see what a race condition is. A race condition occurs when the correctness of a program depends on the timing of thread execution. Two threads race to perform operations and the outcomes depends on who wins. Imagine a simple operation. Check if value is positive, then subtract 1. This is the operation. In sequence code, this is fine because you check the value, then you subtract, and then it's done. But in concurrent code, it's a disaster. That's because, let's say we have two threads A and B, and first thread A checks the value and it sees 1. At the same time, thread B checks the value and it also sees 1. So both of these threads sees the value 1. Then thread A decides to subtract, and at the same time thread B also decides to subtract. Both of them have decided to subtract at the same time, and because of this the value will go negative. This is called a check then act race condition. The check and the act are not atomic, they can be separated by a thread switch. Your invariant says tokens can never go negative. A race condition violates that invariant in a way that's incredibly hard to detect. You may ask why AI fails at concurrency. AI learns from patterns and not principles. AI has seen millions of lines of sequential code. It's excellent at predicting what comes next in a sequential flow, but concurrent execution isn't sequential. It's interleaved in unpredictable ways. AI doesn't simulate execution. When you read concurrent code, you have to mentally simulate multiple threads running simultaneously. You think, what if thread A pauses here? AI doesn't do this. It just generates a plausible looking code. AI's training data is full of bugs. Most concurrent code on GitHub has bugs. AI learned from these buggy examples, so it reproduces those bugs are confidently. When you ask AI to make code thread safe. It will add something that looks like protection, maybe a keyword here, a structure there, without understanding what actually needs protection. Your job is to understand what thread safe actually means and verify that the protection is real. So here is the problem you will be solving in this assignment. Your rate limiter from assignment 2 and 3 is not thread safe. It has multiple threads called try acquire method simultaneously. They can violate the no depth invariant through race conditions. Your requirements are multiple threads must be able to call try acquire simultaneously. The no depth invariant must never be violated regardless of the timing, and also no deadlocks. Your code must never freeze, and also you must make sure that your contract from assignment 3 still works. So what you need to figure out here is what operations need protection, what kind of lock is appropriate, and also where exactly does the critical section start and end. How do you test that protection is working? I'm not telling you the answers. You need to reason through this yourself. AI will give you answers, and most probably the answers will be wrong. Your job is to verify. So next we have the testing challenge. Here is what makes a concurrent bugs terrifying. They don't always appear. You might run the code 10 times and it works perfectly. Run it the 11th time under some slightly different system load and it fails. Let me show you an example. We are running the test 20 times and it might just randomly fail at some run 5. This is why you must run your stress test 20 consecutive times, not once, not 10 times, 20. If any run fails, you have a race condition, you have to go back and fix it. The test suite includes 3 types of concurrent tests. First one is the stress test, 50 threads, and also we have 100 requests each. And then we have invariant monitor, that is continuous checks that tokens stay non-negative, and also we have deadlock test, verifies your code doesn't freeze. You must pass all 3 tests. This is all about assignment 4. Let us meet again in assignment 5. Thank you.